Okay. So yesterday we saw what happens as x approaches the asymptotes. We saw a method that we could use to see how the graph behaves as it gets closer and closer to the asymptotes. So now what happens as the graph approaches both positive and negative infinity? So if we have the function f at x equals x squared plus 2 all over x squared plus 1, and we plug those values in for either positive x or positive values or negative values, because the x is squared in both the top and the bottom, you can see what's happening from the table of values, that f at x is approaching a value of positive 1. So as x gets larger, f at x approaches 1, and as x gets smaller, f at x also approaches 1. So because of that, the limit as x approaches infinity of x squared plus 1 over x squared minus 1 is 1, and we have a horizontal asymptote at y equals 1. If the limit as x approaches infinity of f at x equals a value, L, or the limit as x approaches negative infinity of f at x equals a value, L, then there is a horizontal asymptote at y equals L. And there are several ways that the graph might approach a horizontal asymptote. Up till now, we've been used to seeing graphs where the graph does not actually cross the asymptote, but we're going to see sometimes that happens, where it might cross the asymptote somewhere and then approach it somewhere else, like that first graph shows, right? Second graph shows the same thing, that the graph crosses the asymptote at one point but approaches it somewhere else. The third graph shows that you can have values on both sides of the horizontal asymptote, but the graph is continually getting closer and closer to the value of L. And sometimes you might have two horizontal asymptotes. So all these things are possible, and we're going to see different examples of these happening. But what you have to remember is that it's possible that a graph may cross an asymptote at one point and then approach it somewhere else. So this example says to determine the limits, state the equation of the horizontal asymptote. So this can be done using the properties of limits. And I think we've already talked about this once before, where we divided each term by the highest power of x and took the limit of each one individually. So let's go through that process again. So this is the way we did it before. We had the limit as x approaches infinity. The highest power on x here is x squared, so that's what we're going to divide each term by as we break this up and take the limit of each individual term. Right, so this is what we did before. And for that first term, the x squareds cancel, and you just get 2. The second term on top, nothing cancels.
Good morning. Could we please have the grade 11s come down to the gym for your registration assembly? Thank you.
Right, so some things cancel there, and then we can find the value of each limit. So the limit as x approaches infinity of 2 is just 2. There is no x there anymore. So it doesn't matter what x becomes. The value of that will always be 2. Now, for the second one, as x gets larger and larger, x squared will even get bigger and bigger. So when you divide a 2 by a number that's getting larger and larger, the answer is going to get smaller and smaller. It'll approach 0. And remember, the limit is what is the value approaching. In this case, as x gets larger and larger, what is the value of 2 over x squared approaching? It's approaching a value of 0. On the bottom, it's going to be 1 because the x squareds cancel completely. So you're just left with 1 there, plus the same thing will happen for the second term on the bottom. As x gets larger and larger, x squared will even get bigger and bigger. When you divide 3 by a number that gets bigger and bigger, it'll get smaller and smaller, and again approach a value of 0. So this gives us 2 over 1, which is 2. Okay, so we did this before. And then we talked about the fact that there was a pattern here. We said that when the degree of top and bottom was the same, all you had to do is divide the coefficients of the terms that had those highest powers. So dividing the 2 by the 1 was a shortcut we used to get the equation of that horizontal asymptote. So for question 2, it would be the same because the top and bottom have the same degree. They're both degree 2. They're quadratics. So the horizontal asymptote will be at y equals 4 over 6, the coefficient of those x squared terms, or 2/3. So that was a shortcut that we saw before that we can use when the degree of top and bottom is the same. Right? That's for the horizontal asymptote. So this next example then says, determine the equation of all asymptotes for each of the following. So in this case here, we may have vertical asymptotes as well as horizontal asymptotes. Remember that your vertical asymptotes come from non-permissive values. The restriction on x here is that x cannot equal positive 2. So that will be our vertical asymptote. And then we'll have a horizontal asymptote as well. The degree of the top and bottom is the same, so you divide the coefficients. And we have our horizontal asymptote at y equals 1. Divide the coefficients. All right? Now for number 2, we can find our vertical asymptotes by factoring the denominator. Right? We need to find the value or values of the variable where the denominator equals 0. And we've done this before. If we factor it, it's much easier to solve that equation. The factors are x minus 3 and x plus 2. So our vertical asymptotes will be at positive 3 and negative 2. Now, to find the horizontal asymptotes, in this case, the degree of the top and bottom are not the same. So we will use the same method that we did above. We'll use the property of limits. We'll divide each term by the highest power of x, which again is x squared. So we'll have the limit as x approaches infinity of x over x squared, all over the limit as x approaches infinity of x squared over x squared, minus the limit as x approaches infinity of x over x squared, minus the limit as x approaches infinity of 6 over x squared. So what now, Jihad? Well, first we'll cancel the x squares and get actually 1 there. Oh, I'm sorry, no, you're right. It is x over x squared, so it becomes 1 over x. These ones cancel, and you're left with 1. These ones become 1 over x, and there's nothing we can do with that last one. So yeah, as x gets larger and larger, 1 over x will get smaller and smaller, and it'll approach a value of 0. So once we see that, that's going to be 0, right? Because the bottom will be 1 minus 0 minus another 0. Doesn't really matter what the bottom works out to be, though, because the top is 0. And so this tells us that the horizontal asymptote is a line y equals 0, the x-axis. And that will always happen when the degree of the top is less than the bottom, 1 less than the bottom. Then the x-axis will be a horizontal asymptote. Okay, so we want to sketch the following by determining the intercepts, the maximum values, and equations of any asymptotes. We only have asymptotes if we have rational functions, so there are no asymptotes for this one. But we can find our x-intercepts because it's already factored for us. We'll have our x-intercept at 3, 0. And remember, because that x minus 3 is squared, that means there's a multiplicity of 2, which means that the graph bounces off the x-axis there. We learned about that in 30-1. Then we have an x-intercept at -2, 0, and at 1, 0. And those will both have multiplicities of 1, which means the graph will cross the x-axis there. Our y-intercept is found by letting x equal 0. So you'll have 0 take away 3 all squared times 0 plus 2 times 1 minus 0. 0 minus 3 is -3 squared is 9 times 2 times 1, which is 18. The point 0, 18 is the y-intercept. Right? So to find our max and min values, if we look at this degree, this is a 4th degree polynomial because the x is squared from the first factor times another x gives us an x cubed times our last x gives us x to the 4th. It's a 4th degree polynomial, and the initial term will be negative because of this negative x in the last factor. So the degree is even, so we compare it to a quadratic, which also has an even degree. Because the initial term is negative, this graph will open downwards. This graph will fall to the left, fall to the right. So again, this is a 4th degree polynomial. With the initial term coefficient less than 0, so therefore the graph opens down. It'll fall to the left and right. So we know that in that first interval, it's going to rise up to a maximum. In the last interval, you're going to have a maximum point, and then it's going to fall after that. But we need to find out what those intervals are. And to do that, we will probably want to have the quadratic in expanded form. So that would mean multiplying everything out. So instead of doing that, I'll just tell you what it is. If you multiply all of those factors out, you will get negative x to the 4th plus 5x cubed minus x squared minus 21x plus 18. So the factored form is helpful to find the x-intercepts. Normally that's why we factor, so we can find those x-intercepts. But to find our intervals of increase and decrease, our max and mins, we need to differentiate, so it's much easier to have the expanded form. Okay, so dy by dx will be negative 4x cubed plus 15x squared minus 2x minus 21, and the critical numbers come where that equals 0. So we got to use our factor theorem, our synthetic division, to factor that third degree polynomial. And our potential integral zeros come from the factors of negative 21, plus and minus 1, plus and minus 3, 7, and 21. Okay, so let's see if positive 1 is a root, which means x minus 1 would be a factor, but we would change it to x plus 1 so we can add as we go along here. The terms are in the proper order. There are no missing powers. We don't have to do any adjustments for that. 1 times negative 4 is negative 4, and we add and get positive 11. 1 times 11 is positive 11. We add and get positive 9. 1 times 9 is plus 9. We add and get negative 12. We don't get 0. So x minus 1 is not a factor. So let's see if x plus 1 is a factor. Again, we would change it to x minus 1 so we can add as we're going along. And that's into negative 4, positive 15, minus 2, and minus 21. Negative 1 times negative 4 is positive 4. We add and get positive 19. Negative 1 times 19 is negative 19. We add and get negative 21. Negative 1 times negative 21 is positive 21. We get our remainder of 0. So this shows not only is x plus 1 a factor, but also negative 4x squared plus 19x minus 21 is also a factor. And that quadratic can be factored Negative 4x times x will give us our negative 4x squared. And this will work if we put a positive, nope. Let's try positive 7, negative 3. So the front terms is negative 4x squared. The outer factors will be positive 12x. The inner factors will be positive 7x. They do add to get positive 19x. And the last terms do give us negative 21. So remember, this gives us our x-intercepts. Negative 1, positive 7 over 4, and positive 3. Your y-intercept is always the constant term. And if you look at the original expanded function, it's at positive 18. The constant term gives you the y-intercept for a polynomial function. I apologize. These aren't the x-intercepts. These are our critical numbers of the derivative. We already have our x-intercepts above and our y-intercept. Sorry about that. So this gives us, again, the critical numbers for the derivative. There are 3 of them. Negative 1, positive 7/4, positive 3. If we choose a number less than negative 1, let's say negative 2, and we plug that into the derivative. So we'll use the factored form. When x is negative 2 plus 1 is a negative value. The second factor is what J had. Why is it positive? And what about the last one? And then what? Which we knew already, because the graph falls to the left. So Brighton, what number would we choose for the next interval? It's not a joke. Sure, we'll play your silly game. Let's go 0. So what will the first factor be? Second factor? Third? And then what? Function's decreasing in that interval. A number in the next interval, we could use positive 2. First factor is positive. Second factor will be negative. Negative 4 times 2 is negative 8 plus 7. And the third factor is also negative. So this will be increasing. And the last one will be decreasing because we know that it falls to the right. But just to make sure, if we choose a value like 4, 4 plus 1 is positive. The second factor will be negative. Negative 4 times 4 is negative 16 plus 7. The last factor will be positive. Again, confirms that. So this also tells us that we have local max and min points. We will have local maximum at f at negative 1 as well as f at 3. And so if you plug those into the original equation, f at negative 1 is positive 32, f at 3 is 0, and we will have a local min. And we could say that the first maximum is actually an absolute maximum because that is the highest value here, but that's okay. Our local minimum will be where x is 7/4, and that point on the graph is y has a value of negative 4.4. So we've got everything that we need to sketch this graph. Right? We have x-intercepts positive 3, negative 2, and positive 1. So we can use a scale of 1 on the x-axis. So again, x-intercepts at positive 3, and that has a multiplicity of 2. Positive 1 and negative 2. Our y-intercept is at positive 18. So I need to change my scale here. Let's use a scale of 6. So that'll be negative 6, negative 12. And our y-intercept, again, is at positive 18. We have a maximum point at negative 1, 32, which is going to be quite high up here. So another one up will be 24. 32 will be approximately right there. 7/4, negative 4.4. 1 3/4, negative 4.4 is approximately right there. And 3, 0. Whoops. And the reason that is a maximum is because that's where the graph bounces off. So the graph comes up to that maximum point. goes down through the y-intercept. It crosses the x-axis at 1 down to the minimum, up to that x-intercept of 3, which has a multiplicity of 2. So the graph bounces off there, and there's a sketch of that graph. So what we did different here from 30-1 is that now we use derivatives. We find the intervals of increase and decrease, which also allows us to find out where those max and min points are. That's the piece that we were missing from 30-1, finding out where those max and min points actually were. So we use derivatives for that. All right, so this next one is a rational function. If we look at the denominator of x plus 2 all squared, we're going to have a non-permissive value here. X cannot equal -2, because that'll give you 0 on the bottom. So therefore, x equals 2 is an asymptote, a vertical asymptote. Also, in this case here, because the degree of the top is 1 more than the bottom, the x-axis, or the line y equals 0, is also an asymptote. Because the degree of the top is 1 less than the bottom, that makes the x-axis, the line y equals 0, an asymptote. Okay, so what about our intercepts? Our x-intercept, again, is where y equals 0. And the rational function equals 0 when the numerator equals 0. The numerator is just x. So when x is 0, you're going to get 0 over, you're actually going to get 0 over 4, which is 0 though. So that is our x-intercept, which will also be our y-intercept, right? The graph goes through the origin. There's only one asymptote here. Sorry, only one intercept here. Goes through the origin, and that's the only intercept that we have. All right, so the other thing we can do is we have our vertical asymptote as x approaches +2. So if we want, -2 I should say. I wrote +2, that should be negative. If we want, we can find the limit as x approaches -2 from the left and from the right. So we can see what the graph is doing as it gets closer to that asymptote. What is the behavior of the graph as it approaches that asymptote? So as x approaches -2 from the left, the top number will approach a value of -2. But as we're approaching -2 from the left, that means like -3, -2.5, -2.1. So that's going to make x plus 2, that gap is going to get smaller and smaller. So those decimals are going to get smaller and smaller. Now they will be negative, however, you're going to square it. So you're going to get very small numbers that are going to be squared. And then when you square it, it's even going to be smaller. So they are going to approach 0. They're going to approach 0, right? But then, because you're getting a number that's getting smaller and smaller, so we can say a small positive. So you're going to be dividing -2 by a number that's going to get smaller and smaller. That is going to approach -infinity. So that's what's happening on the left side of -2. If we find the limit as x approaches -2 from the right side of x over x plus 2 all squared, so again, the top number will approach a value of -2. The same thing's going to happen on the bottom, okay? But now we're to the right of -2, so you might have -1, -1.5, -1.9. Again, that gap is going to get smaller and smaller. This will give us, though, a positive decimal on the bottom, but it's going to get to be a really small number. And when you square it, it's going to get even smaller still. So again, it's going to be a small positive. And when you divide -2 by a number that's getting smaller and smaller that remains positive, again, this will approach negative infinity. So the two-sided limit exists for this one. It approaches negative infinity on either side of the asymptote. Okay, so now we're going to find our intervals of increase and decrease. We're going to find the derivative, which in this case we'd have to use a combination of laws. The quotient rule, which means the derivative of the top times the bottom. So that's that step. Minus, when you differentiate the bottom, you have to use the chain rule. So it's 2 times x plus 2 to the power 1 times the derivative of what's inside, which is 1, times the top, which is x. All over the bottom squared, which will become x plus 2 to the 4th. So to differentiate, we have to use the chain rule here when we do the bottom. So it's a combination of the quotient rule and the chain rule. So again, just to check that. Derivative of the top is 1 times the bottom, minus derivative of the bottom, which we use the chain rule for, and that has two parts, the power rule, as well as the derivative of what's inside the bracket, which is just 1, times the top, which is just x. Now, we can simplify this a little bit. So we're going to have x plus 2 all squared Now I'll have -2 times 1 times x, which is minus 2x bracket x plus 2 all over x plus 2 to the 4th. And before we multiply everything out here, there is one factor of x plus 2 in all three terms. So we can divide all three terms by a factor of x plus 2. That'll get rid of the squared on that first term on top. It'll eliminate the x plus 2 in the second term, and on the bottom, the power 4 will become power 3. So this just allows us to simplify this expression. We've got x plus 2 minus 2x over x plus 2 cubed, which gives us negative x plus 2 on the top all over x plus 2 all cubed on the bottom. This is the derivative, right? And remember, the critical numbers for the derivative happen at two spots, or two cases. The first case is where the derivative equals 0, but the second case is also where it is undefined. This is a rational function. A rational function equals 0 when the top equals 0, where negative x plus 2 equals 0, or where x equals positive 2. That's a critical number. Also, where it's not defined will be where x equals negative 2. Something's going to happen there. But we already know what that something is. That something is the vertical asymptote. We already know that. At x equals negative 2, there's a vertical asymptote. But now we have to see what's happening at x equals positive 2. If we choose a number to the left of positive 2, a number like 0, what's happening to the derivative? So again, I'm going to use this expression right here. That's my simplified expression for the derivative. So I can let x equal 1. I'll have -1 plus 2, which is positive. The bottom will be positive, so the function is increasing in that interval. When x is greater than 2, a number like 3, the top will be negative. The bottom is still positive, but this is going to give us a decreasing function. So therefore, there is a maximum point at f at 2. And when you let x equal 2, you're going to get a y value, which is quite small. It's going to be 1 over 8. So, what do we got here to do our graph? This thing. So if I look at what I need to put on here, I need to put a vertical asymptote at -2, a horizontal asymptote on the y-axis. So there's our vertical asymptote. There's our horizontal asymptote. We also saw that we have a maximum point, a local maximum at the point 2, 1/8. So because of that, I'm going to need to use a fairly small scale on the y-axis. Maybe I'll use a scale of, I don't know, 1/4, 1/2, 3/4. Because I need to show a point y equals 1/8. The point 2, 1/8 is a local maximum point. So according to the scale that I chose, that's going to be that point right there. We saw that the behavior of the graph as it approaches the vertical asymptote is that it's approaching -infinity. So this graph will look something like this to the left of that asymptote. It'll also approach the asymptote on the right side as well. Remember, we said that the origin is our intercept. So this is an example where the graph is going to approach the asymptote at one point, but go through it somewhere else. Because it's going to go through that point, it's going to come up to my maximum, and then it'll approach the asymptote as we go to the right. And you could confirm that by choosing values of x that get bigger and bigger and plug it into the equation. If we let x get larger and larger numbers, you'll see what's happening to the value of y. So for example, if I let x equal 10 in the original equation, it'll be 10 divided by the bracket 10 plus 2 squared. I guess we can just go 12 squared. Right? It's a decimal, a positive decimal, 0.069. If I let x equal 100, it'll be 100 over 102 squared. Still positive, but closer to 0. If it's 1,000, it'll be 1,000 over 1,002 squared. Now it puts it in scientific notation. 9.96 times 10 to the -4. Still positive, but even closer to 0. As x gets bigger and bigger, the value of y will approach 0. And so that's how we know that it's approaching the asymptote as it goes to the right. But it crossed it over here because the point 0, 0 is a point on the graph. It is our intercept. Okay? So you should be working on page 223, questions 3, all of 3, and then on question 4, A through D. And this thing is really lagging today. A through D, as well as F and H. So I looked, we're not going to be done this chapter before the break.
Pardon the interruption. Could we please have the grade 12 head down with their class to the gym for the registration assembly? Thank you.
I think it's a graduation assembly.
Oh, this, there you go.